Good morning and good afternoon, everyone. We'll get started in a couple of minutes. We'll give it about 3 more minutes and see if more people join. It's almost noon. Hello, everyone. I'd like to welcome you to the latest ECSS Symposium, and I'd like to welcome our guest, Professor D.K. Panda at The Ohio State University. Professor Panda, I guess, has been involved with HPC for quite a long time. I know the whole time I've been at TAC, we've been using his group software, the MVAPICH2 software, to run on all of our systems. And his group has developed this software over the years with an emphasis on performance, I'd like to say, starting with, I guess, InfiniBand. And it has served us very well. I see here that you've got it installed in over 2,500 organizations worldwide in 79 countries. It's quite impressive. And so today, Professor Panda is going to speak to us a little bit about how we can tune our codes to get more performance from the MVAPICH2 software. And I'd like to welcome you to the symposium, Professor Panda.
Okay, thanks, John.
Thank you.
For the kind introduction. Good afternoon to the East Coast folks and good morning to West Coast folks. So it is a pleasure to be participating in this seminar series, and mostly we'll go a little bit into depth of how to tune and extract higher performance with MVAPICH2 libraries. As most of us know, these days, if we take a look at all the modern HPC clusters, like starting from Stampede at TAC to Tihanhe 2 in China, Tihanhe 1A, and also Titan, broadly we see these are commodity clusters consisting of multi-core and many-core technologies. Also, they are using high-performance connects like InfiniBand with RDMA access, and also these machines have accelerators, either NVIDIA GPUs or Intel mic. And of course, some of the systems and the upcoming systems are coming up with SSDs, NVMe SSDs, NVRAM, etc. Now, the major question the community has been working over the years saying, what is the right parallel programming model? Of course, we have different kinds of models. Most common one is the MPI, which is the message passing interface, which supports basically distributed memory model. On the other extreme is the cache coherent shared memory model, which is the typical SMEM or DSM, and they are mostly available on small scale of nodes, but they don't scale very well to very large number of nodes. So this is where the new thing is emerging called PGAS. Many of you must have heard of this. It's a partition global address space. So it basically takes the
Sorry, Dr. Panda.
The distributed memory perspective and trying to. Yeah, was there a question?
I was just going to request that please people to mute themselves because there's a lot of background noise.
Okay, thank you.
Themselves. Thank you.
May I request you people to mute your mics and then also the cell phones, everything. Thank you. So I was discussing about the PGAS, and that is kind of the paradigm which is coming. So as John indicated, especially in my group, we have been working in this area for almost now 25 years. In fact, when InfiniBand came into the picture in the year 2000, we were the first ones to actually start working on it, the MPI for InfiniBand. Prior to that, we were working on the previous cluster technology like Mirinet, Quadrix, IBM I think once again, may I request people to mute themselves. Thank you. So we made the first release of the MPI for InfiniBand in the year 2002, and then after that we have been continuously extending it to have it for 10 to 40 gig IWARP, also for RDMA over converged enhanced Ethernet, the Rocky, and we also have the hybrid version which is for MPI and PGAS, focusing also on the GPUs, mic, virtualization, as well as the energy awareness. And this stack has been growing over the years. Currently, it's being used by more than 2,550 organizations in 79 countries. And these are again based on the voluntary registration on our site. And recently, we crossed almost 363,000 downloads from the OSU site directly. Our stack is also integrated with a lot of other kinds of distros like Red Hat and SUSE. And not only it's being widely used, it is also empowering many top 500 clusters. Just to name a few, like the Stampede, Manasa, Pleda, Subami, a lot of these large-scale systems are using our stack. And we have been in this community for almost now 16 years. If some of you remember, like the System X from Virginia Tech, that was the very first InfiniBand system, which was number 3rd in the November 2003 list. So that was actually enabled using MVAPICH2 stack. That time, in fact, it was MVAPICH1. And then since then, continuously over the last 16 years, we have been empowering a lot of these systems. So broadly, the next slide, which is trying to show the overall MVAPICH2 architecture. So at the top level, we have not only support for MPI, we also have support for PGAS, pure PGAS like UPC, OpenSMEM, ORA Fortran. Recently, we even added UPC++, and also we have the support for hybrid versions. So you can actually run both MPI plus OpenSMEM, MPI plus CAP, plus UPC++, even the very simple one, the MPI plus OpenMP. So then at the lower bottom, we have the support for all different kind of networking technology like InfiniBand, IWARP, Rocky, and the latest release, we also introduced the support for OmniPath. And also on the right-hand side, we support all the different modern multi-core, many-core architectures. In fact, in the latest release, we introduced the support for open power. And we try to exploit a lot of these different kinds of transport protocols, their network features, transport mechanisms. And we are also looking forward to a lot of these upcoming features like MCDRAM, NVLink, CAPI, etc. So broadly, the middle layer, that is our the design which we put in. It has a lot of these point-to-point collectives, energy awareness, all these features. And this is where we'll be talking a little bit later how you can tune the stack or optimize it for your applications to get the best performance. So the next slide is actually trying to show just a kind of a timeline and downloads. Over the years, we have been continuously making newer releases, and it's being very widely being adopted in the community. So broadly now we have we call it like a MVAPICH2 software family because it is like the technologies are moving so fast. People want the best solutions for their kind of an environment. And sometimes based on the Linux distributions, the features, the OFED, they actually conflict with each other. So we have the basic MVAPICH2, but at the same time, we also have the MVAPICH2X, which supports some advanced MPI operations, the PGAS, MPI-PGAS. It also has support for VoiceU. Is a new project we have started, the InfiniBand network analysis and monitoring. And then we have the specialized version for GPU, that is the MVAPICH2 GDR stack. Similarly for the mic, we have MVAPICH2 mic, virtualization with SRIOV, OpenStack. We have MVAPICH2 virtualization. And around 6 months back, we also made a new release, which is purely energy aware MPI. So that means if you want to actually conserve energy within the runtime, we have a lot of new designs. So these are all the different libraries, but today we'll not have time to go over all those things. So primarily, I'll be talking about the MVAPICH2, little bit of MVAPICH2X, and then MVAPICH2 GDR. So these are the stacks which we'll be focusing next. So just to give a background, just the way we actually approach this problem, how we design these libraries, we of course first do the research. Many times when we explore the designs, they are first presented to conference and journal publications, and then the best performing designs are incorporated into the code base, and we take the code through a very rigorous QA procedure, including like exhaustive unit testing, different kinds of test procedures for a range of platforms, interconnects. Then we do a lot of performance tuning, application-based evaluations, and also we do evaluations on larger scale systems before pushing out the releases. So even the alpha and beta versions go through the above testing sequence. So we encourage people to even use the alpha and beta on their systems to exploit the latest capabilities in terms of performance and scalability. So with that kind of a background, what I want to focus on the runtime optimization and tuning flexibility. So we'll start with MVAPICH2 and MVAPICH2X libraries. So we'll focus on 5 different aspects: the job startup, point-to-point internode protocol, transport type selection, and then the point-to-point intranode protocols and collectives. Of course, there are a lot of other issues like the RDMA, checkpointing. Those, due to lack of time, will not be able to go into detail. And then I'll be talking about the MVAPICH2 GDR, which focuses on like CUDA aware MPI, GPU direct RDMA feature, and the corresponding tuning and optimizations. And then I'll try to conclude the third part of the talk, which is like the application best practices. So in this context, over the last few years, we have been working very closely with Tax Stampede folks, SDSC folks, as well as Ohio Supercomputing Center. So we are trying to bring a lot of practices in terms of like which parameters actually work out the best on which system. So I'll try to give an overview of around like 8 different applications. Illustrate the concept that one can actually do a lot of optimizations to get the best performance on Exceed and as well as other kinds of systems. So this is as some of you might be knowing, we have the MVAPICH2 stack has a lot of different kinds of interfaces. The common ones are the default ones are the CS3, that is the OSU enhanced the CS3. And under that, we have the IB support, iWarp, Rocky, the TrueScale, the old one, as well as the OmniPath with PSM2. And we have shared memory and TCP/IP. We also have the support for Nemesis, and it supports all different PCI interfaces and the platforms. And with respect to process managers, we have a lot of flexibility. The best one is, of course, the MPI Run RSH, but we also support the MPI Run, MPI Exec, MPI Exec Hydra, and we also have very good support for Slot. So if some of you are on our mailing list, you would have seen like around 2 weeks back, we made a MVAPICH2 2.2 RC1 release. So here we introduced support for open power architecture, also support for Intel OmniPath architecture, also support for the Rocky V2. And we have done some, especially for OmniPath, the PSC, the new Bridges system. We have done some architecture detection, and we are working on some further tuning on that. And then, of course, it has a lot of additional features like the startup performance, optimized point-to-point collectives, and additional ones. So let's go into details. Of course, on any system, first you can install it. We have a set of different kinds of parameters like configuration parameters as well as runtime parameters. And even like the sysadmins, when they want to install on their system, they can actually utilize some of these guidelines, which I'll be mentioning, to have a best environment for their system. But on top of that, at any user level, we have a lot of user configurable like the runtime parameters, and those parameters can also be used to make it customized or optimized for any particular given application. Because when we make the releases, we do a lot of architecture detection and tuning, but as you know, this is a general purpose package, and a lot of architectures are evolving. All the platforms are very different. So we take it through a reasonable kind of tuning, but then after that, of course, we cannot optimize it for every platform and every application. So this is where this seminar is meant for the sysadmins as well as the end users to utilize some of these parameters to extract higher performance from the MVAPICH2 installations on various systems. So we'll start with job startup. As many of you know, as system sizes are continuously scaling, it is becoming a challenge to even to just to the startup MPI job. If some of you go back, in fact, around 10 years back when the Ranger system was being deployed at the TAC, at that time, I mean, there was no MPI stack which was able to even to scale to that system. Just the job was not even starting. So over the years, of course, people have been deploying larger and larger systems. So we have been working on bringing newer kinds of solutions. And the solutions can be actually indicated in two dimensions. One is, of course, the x-axis. Here we are showing the job startup performance. That means the higher it is better. But at the same time, we're also trying to require or coming up with solutions so that we require lower and lower memory footprint, so that the job itself or the MPI runtime doesn't take a lot of memory and is trying to give more memory to the end users. So over the years, like these are the A, B, C, D, E, these are the different kinds of new designs we have carried out, which have been published, and at the same time have also been incorporated into the distributions. And with the latest design, we can actually get very near constant MPI and OpenSMEM initialization time. Up to 16K processes, we see almost like a factor of 10 to 30 improvements. And at the same time, the memory consumption has been reduced with order of processes per node. And for example, like if you even try to scale to 1 million processes with 16 processes per node, we have the latest design can actually save 1 gigabyte of memory per node. So the way we try to go through it, I'll go into a little bit more details. Broadly, we support all different kinds of job launchers. We have the core launchers as well as the wrappers and interfaces. Our core launcher is MPI Run RSH. That is the kind of a default and the preferred launcher for all interfaces, and that supports the scalable hierarchical job startup and mechanisms. We also support the MPI exec Hydra from ANL. We also have support from MPI exec and MPI exec MPI Run RSH. And in addition to that, we also have compatibility with external resource managers, especially Slurm and Torp. And we have been working with a lot of the PMI interfaces and enhancements with respect to Slurm, which I'll be mentioning in the next few slides. So with respect to job launch, we have a separate a set of runtime parameters, because how you actually start up the job, whether it is what kind of tree you use, there is some threshold beyond which the hierarchical SS scheme is used, a number of process thresholds. We also have a parameter for homogeneous cluster. These days, as some of you know, the large clusters are mostly homogeneous, but many times the small clusters could be heterogeneous. That means some nodes can have like a DDR cable and some can have FDR cable. So of course, we have internal designs to detect the heterogeneity and make sure that the job runs properly, but we have a special flag. So if your system is homogeneous, we actually strongly suggest you to use this MV2 homogeneous cluster flag, and you will see your startup will be significantly improved. So all these are again runtime parameters for different system sizes and different networks. you yourself can actually play around with it and see which set of parameters actually works the best for your system. So here, these are some of the numbers where we have recently been working with a tight integration with Slurm. So if you take a look at this, what we are showing in this graph is the x-axis is the number of processes, and then we are trying to show hello world, and the MPI init as the time which gets spent in the MPI init. So the red lines are actually with the MVAPICH2 2.0 version with the default Slurm, but if you see like a 2.1 and the recent versions, where we have done some optimizations, not only with our stack as well as the Slurm stack, and then you can see like we can gain on almost like a MPI init time is improved by 59 times at a 8K processes. Similarly, hello world time is also reduced by 5.7 times for 8K processes. And these are all the new designs which are available in the latest version, and especially with the MVAPICH2 2.2 RC1. We introduced this new optimizations. We call it like a SMEM PMI. That is the process management interface over shared memory. So here we try to actually use a single copy per node so that we can have a reduction of like order of processes per node. And here it shows some of the graphs, like you can see the time taken by one PMI gate. We can get a significant improvement, almost by a factor of 1,000. The number of processes per node keeps on increasing at a 32 processes per node. And as you know, we are entering the field where more and more nodes are becoming more and more number of cores. So this kind of optimized designs actually not only will help the modern systems, but also the next generation systems. And the right-hand graph is actually trying to show the memory usage per node. And as you can see, we have done experiments up to 16K cores. And then the right part is the estimated one. And here you can see like almost a factor of 16 improvement we can provide about memory usage per node. And all these enhancements, actually, we have made them available. So when you download the MVAPICH2 2.2 RC1, there is also a Slurm patch. This patch is for Slurm 15.08 version. So you should be able to download that and then work it in your Slurm environment together with our MPI stack to get this kind of the good performance and scalability. So let me move ahead now. That is the job startup part. But when, as you know, when the jobs start running, we want to make sure that the job, any given job runs with the best possible performance. So that comes to the first, the point-to-point internode performance. And as many of you might be knowing, MPI internally has two kinds of protocols. One is called eager, that is typically gets used for smaller messages, and internally there are some copy-based schemes get used. And the other one is called the rendezvous message, which are for the larger one. And of course, for at some message size, we need to switch between eager and rendezvous because you can see from the left-hand graph, as the message size increases, at some time, because of the memory copy overhead, the eager time takes more than the rendezvous, even though the rendezvous has some few additional handshake messages. So then the question is, okay, how do we select this? And over the years, what we have done is we have done a lot of architecture detection. This depends on your processor speed, your network speed, your network adapter, the memory speed, with a lot of factors. And the right-hand graph is trying to show the impact of the eager threshold. So depending on the eager threshold, you will see that the medium message sizes will have different kinds of performance. And not only you have the impact on performance, it also has an impact on memory footprint, because the more eager threshold size you go, you will be needing more and more memory space, and that will actually increase the memory footprint. So in all the releases, we do a lot of tuning for all different kinds of platforms. So these are automatically done internally. So when you install your system or the library, it automatically detects the best one, but the best one when it's safe for that platform. So that need not match with your application characteristics. So if your application, let's say we put a threshold of 16K, but for your application, the most common message size is 17K. So then you will see that you may not be running it in the best possible manner. But at the same time, if we can push then for that particular application, this eager threshold, we can push it to 17K or 18K, you may see that your performance may increase. So that's what we show in the lower part. Any job you should be able to run with a runtime parameter called MVAPICH2 IBA threshold. So based on the characteristics of your job, you should be able to play around with it and get the best performance. So even in the internode point-to-point tuning also, we have two additional mechanisms here. One is called the RDMA first path. This is a design which has been there from the very beginning of our stack, which does a lot of optimized communications for those processes which are frequently communicating, so that we give more priority to them to get the best performance. So that is, you can see on the left-hand side, using RDMA first path, you can actually get improvement in latency. And at the same time, we also have for this RDMA first path different set of buffers. We call it a window size. The default is 64, but as you can see, like this has some sensitivity depending on, let's say, you increase the number of buffers from 8 to 128, you can see actually your message rate will improve. So if your application is again uses a lot of short messages and it has it's sensitive to the message rate, so you can play around with this parameter to extract higher performance. And also there are two kinds of rendezvous protocol. One is a GET protocol, and as a PUT protocol, the default is RPUT. But also with the runtime, you can now actually switch to RGET. So that actually can help you in some cases based on the sender and receiver characteristics, like who comes first, who comes second, kind of things. You can see different performance benefits with these two different protocols. So then let's move to the transport type selection. As many of you might be knowing, the InfiniBand, when it started with the basic two protocols which are commonly used, like RC, which is reliable connection, and then the UD, which is unreliable datagram. And at that time, there was only individual queues for every process. But then as the technology matured and then larger and larger systems were deployed, there was a newer mechanism which was introduced called shared receive queues. So that means using the same shared receive queues, multiple processes can communicate to a same process. And you can see here, using that SRQ support, you can significantly reduce the MPI init memory utilization, both on the left-hand side, which are based on the actual experiments, and the right-hand side, which is an analytical modeling, so that it can actually reduce the memory usage by almost 1/6 at 64K processes. So we have that support. By default, it is enabled. MVAPICH to use SRQ, it is always enabled. But we also have two additional parameters for users to play around, especially when you are running larger scale runs. You can actually try to increase this limit so that MVAPICH to SRQ max size and MVAPICH to SRQ size, this can be tuned to get even higher performance from your application. Then the InfiniBand standard also moved into, the RC was actually based on point-to-point connection, like from process to process. But when multi-core started coming, the InfiniBand consortium introduced a new protocol called XRC, which stands for Extended Reliable Connection. So what it does, it actually tries to establish connection per node, not per process. So from a single node, any process from a given node can actually use the same connection to communicate with the other node. And that also helps with significant memory reduction. You can see on the left-hand side the number of connections. With increasing the number of connections, we can significantly reduce the memory. And it also helps sometimes, in fact, in also performance, because especially the way the adapters are designed these days, they typically do some kind of a caching they have for the number of connections. When the number of connections are too large, then you go through some kind of a cache thrashing. So if you can reduce the number of connections, you actually gain performance. Now, this XRC support, when it was introduced, it was not there in the original OFED. Gradually, it has come to the recent OFED. So that's why, by default, we disable it, just to make sure that it doesn't break on any system. But we strongly recommend you to use this XRC on, so that you can run it on a multi-core environment. So there is also the other transport protocol I indicated, unreliable datagram. So there is a reliable connection. So there is a connection-oriented mechanism, but it is reliable. But there is also a unreliable datagram, that is like a UDP protocol, and RC is like the TCP protocol. So there is a trade-off in the memory footprint. You can see the UD ones broadly have like a very constant memory footprint, whereas the RC ones, like the memory footprint increases. So we have the support for both the RC and UD, as well as there is a hybrid, which I'll be talking in the next slide. And you can actually run jobs. For example, you can say MVAPICH to use only UD. By default, it is disabled, where RC and XRC are not used. But if you want to run with UD, and in fact, later on I'll show, you see benefits with this mode for some of the applications. Then you can also do UD zero copy. Depending on your system size, you can try UD retry timeout or retry count to get different kinds of performance. So then, since we have the UD mode, we also have the RC and XRC. Many years back, actually, we introduced, since MVAPICH 1.7, as a hybrid mode. So you can think of it like a hybrid vehicle, just like we see these days, which has a good balance between the consumption of gas and electricity. Similar kind of things we can do internal to the MPI stack to have a good performance, as well as to have a good memory footprint. So that is actually, you can figure it with, you need to configure, there is a configure flag, you need to do enable hybrid, and then also at the runtime, you can enable or disable the support using MVAPICH to use UD hybrid. Then there is a threshold size, because this scheme has some overhead, so we don't turn it on for all job sizes, especially let's say your job sizes are larger, you should see good benefits with this hybrid scheme. So currently the default is 1024, but once again, this is a runtime parameter, so you should be able to move around that to match with your application characteristics, and also you can vary also the max RC connection. And here we are showing, for example, if you think of like a HPCC random ring, which is a very common benchmark, you will see that you can get the very good performance with the hybrid design. It is always the best of the UD and the RC. And over different like number of processes here, you can actually get like a benefits from 26 to 40%. So then recently, Mellanox has introduced another new scheme for direct connect for DC transport. And we have actually support for this in the MVAPICH2X stack. So it actually does some newer kind of way. For example, it just talks to the adapter, and then the adapter talks to the remote processes. And if the connection is not, or if no data transfer is taking place, it can actually tear down the connection automatically and then switch to another connection. So these are the kind of a new mechanism. And if you see, you get significant benefits in memory footprint. The left-hand bar, if you see the connection memory, the red one is the RC, and then this is the blue is the UD, the pink is the XRC, but the green one is actually the new design, the direct connect. And that also has impact on the performance. If you're on the right-hand side, you will see with the NAMD APOA 1 large data set, you can get this. So this is the newer scheme. So if you have the systems being deployed with Mellanox OFED, that is where the support is available. So you should be able to utilize that together with our MVAPICH2X stack to get higher performance. So then let me move ahead. Similar kind of things also exist for intra-node protocol. As you know, as the number of cores per node are increasing, in fact, in any reasonable job, in fact, a lot of MPI communications happen within the node. So unless you do good optimizations there, you don't see good performance. So we have actually the basic scheme, which is a shared memory 2 copy. That means process 1 writes to the shared memory, process 2 reads it. But over the years, we introduced a new kernel-based module scheme, which is like a LIMIC2. We called it. It's actually it tries to achieve a single copy. So you can register your sender address and pass it to the receiver so that the receiver goes and directly reads it. So that scheme has been there for many years, and recently similar kind of schemes has actually come to the standard Linux kernel. The support is called CMA, cross memory attach. So we actually support all these 3 things. And here you can see like from the graphs, like the bandwidth and bidirectional bandwidth. If you use either LIMIC or CMA, you get much more benefit, especially for large messages. So we support both LIMIC2 and CMA. you can actually configure with the appropriate flags as indicated here. And we strongly recommend users to turn on any one of these to get the benefits for large message exchange. And there are some rules here. If both the LIMIC2 and CMA are included, then LIMIC2 is chosen by default. And whether neither is selected, then shared memory is chosen, but then you may not get the best performance. Now, just like the inter-node communication and the intra-node also, we have a few additional parameters here. One is called the threshold, and there is a length, then there is a number of the buffer and the size of each buffer. So all these actually play a role to have different kinds of behavior in the intra-node. So you can actually adjust the eager threshold and eager buffer size. Again, just like the runtime parameter, that will affect the performance of small messages and memory footprint. Similarly, you can also adjust the number of buffers and buffer size for the rendezvous protocols. So if you see that for your applications, you have a lot of communications going on intra-node, we strongly recommend to play around with these parameters. Of course, we have done with our releases based on the platform, we do some kind of tuning, but it can also be optimized further to match with the characteristics of your applications. So that's what is shown in the next slide. So these are like, if you see the Intel Sandy Breeze, Bulldozer, different kinds of behavior we see for bandwidth, bidirectional bandwidth. We do a lot of exhaustive architecture specific tuning, but we also have the freedom so that the end users can actually also change these things. So with that kind of a background on the point-to-point, let me move to the collectives. As you know, the collectives in the MPI take a lot of time, and there are all different kinds of collectives. So we have our design, a range of collective options are there. So not only we have the conventional flat scheme, but also we have multi-core aware designs. And multi-core aware designs, we have the different paths like the inter-node communication. Either we can use the point-to-point, or we can actually use InfiniBand hardware multicast. I'll be talking about that next. And within intra-node, we also have intra-node point-to-point, intra-node shared memory, and intra-node kernel assisted. So most of the modern systems, since multi-core is there, we go through this multi-core path as well as the shared memory. So that's why the MV to use shared memory collective, that flag is always on. And some people actually use very well the hardware multicast scheme. I'll show some numbers next. But some people don't use it, so that's why we have it's like there is a flag MV to use multicast, which is default off, but we again strongly recommend people to turn it on. So these numbers are taken on Tax Stampede. InfiniBand has a hardware multicast scheme where the copy actually gets done at the switch level, and to give you very good performance. So here if you see like 102,000 cores, instead of the traditional k-nomial algorithm, using the multicast scheme, we can improve the latency of MPI Bcast by almost 85%. And similarly, here we see very good scalability. Like as we increase the number of nodes to 6K, we see very good, within 5 microseconds, we should be able to even send the data to all the nodes. So it is not only useful for the hardware multicast. In fact, we have internal algorithms which takes advantage of this feature. So here it shows like, for example, scatter. Which is again a common collective operation. If you use the hardware multicast based design, you should be able to even improve by 57%, 75% kind of things. So that similar kind of designs are also applicable to all reduce. So again, broadly, we have this flag, which is MVAPICH to use MCAST1. That should enable the hardware multicast feature. As I indicated earlier, it is disabled, but some systems it is enabled like Stampede. So we strongly encourage you to configure with this enable MCAST flag and then turn on the multicast runtime flag to get the benefits of hardware multicast for all the collectives. Then for the shared memory aware collectives, as the multi-cores, based on the number of cores and all, we keep on optimizing our design over the years. And here you can see like you get like MPI reduce, all reduce, barrier. There is a big performance improvement when you use the shared memory aware collectives versus the non-shared memory aware. So in all our recent releases, the shared memory is default, so you don't have to do anything here. So then the question is, those are like the blocking collectives. As many of you know, there's a MPI-3 standard has introduced non-blocking collectives. So we have been supporting that since MVAPICH2 1.9. So in this case, there are different kinds of solutions. For example, you can use MPI-3 collectives with either the Gen 2 or the Nemesis interface. The internal implementations can be done in a multi-core aware manner or hierarchical or a basic flat approach. But the main thing is to have, in fact, we have advanced designs which not only takes the non-blocking collectives, but it also uses the core direct support. That is the feature with the latest InfiniBand adapter, where the adapter can actually make the progress of the non-blocking collectives. Because always with the non-blocking collective, the challenge is who is making the progress. If the core is trying to make the progress, then you don't get the good overlap of computation with communication. Whereas if you can do the core direct from the adapter, you get very good overlap of computation and communication. So in this case, so this support is already available in the MVAPICH2X for the last year. And what we have trying to show here, in fact, we have done some core designs working together with the application scientists, because to use non-blocking collectives, you have to modify your application also. So we have done the application modification as well as the design changes in the MPI runtime and using the core direct. So that is a 3-layer core design. And here you can see that the end applications, for example, P3DFFT, we can get 17% benefit. PCG solver, we can get 21% benefit. Even for HPL, we can actually give you 4.5% benefit. So if you have some advanced applications and you are ready to move to non-blocking collectives, or you are using also non-blocking collectives, I'll strongly suggest you to use this design so that you can actually get a lot of overlap with computation and communication and get scalable performance for your application. So those are the kind of the broad MVAPICH to MVAPICH2X tuning. So let me move into the MVAPICH2 GDR library. This is primarily being targeted for the GPU clusters. As many of you might be knowing, over the last several years, the GPU accelerator-based systems are growing over the years. So we introduced, like around 4 years back, we introduced the concepts of CUDA-aware MPI library. So the idea is that typically most of the time, if you take a look at the right-hand side, we have a GPU here, then InfiniBand, sender and receiver. Typically people do a CUDA mem copy to take the data from GPU buffer to the host, then do the MPI, and then do again the other side, the CUDA mem copy. So we introduced the GPU-aware MPI library so that just like you do MPI send and receive from host memory, you can actually do MPI send and receive from GPU memory exactly using the same construct. So that means the end users even doesn't have to touch CUDA, and everything else gets done inside the library. So if you see the animation here, internally we actually move the data from the GPU buffer to from the sender to the receiver using the best kind of a communication paths and with the best set of parameters within the MPI library. And that leads to actually high performance and high productivity. We introduced this concept and we have extended like 2 years back. The newer technology came called GPU Direct RDMA or GDR. So what it actually helps, if let's say, for example, your GPU adapter and IB adapter on the same PCI Express, you can actually move data back and forth between these two devices without going to the host memory. But conceptually you can do that. But if you take a look at some of these numbers here, like the green path, like reading from InfiniBand or network and writing to the GPU, you get very good bandwidth. But when you're reading from the GPU memory and pushing it to the network, you get very poor bandwidth. And this is valid for both Sandy Breeze as well as Ivy Breeze. And this is nothing to do with the NVIDIA or Mellanox, but it is a limitation of the chipset, which is being used by the Intel platforms. So in order to handle that, we have some kind of a hybrid design so that for different message sizes, we use different protocols. So this CUDA-aware MPI has been there for many years, starting from version 1.8 to the latest 2.2. So not only we optimize all the point-to-point paths, we also take advantage of CUDA IPC. We have done a lot of optimization on collectives, data type supports. So the latest numbers, if you take a look at, these are very impressive numbers. So for example, let's say GPU to GPU internode latency, you can see that this black line is without GPU direct RDMA. In our earlier 2.0 version, we reduced the latency to this blue line, and since last year, with the 2.2 series, we have actually reduced this red line. So think of this number, which is 2.18 microsecond. So effectively, InfiniBand these days provide like a 1 microsecond, and we put like take another 1.18 microsecond to move data from GPU to other GPU. So I'm very proud of my team who have done all these designs. In fact, to get this kind of performance, you cannot get this kind of performance with any other MPI stacks which are available in the community. So that leads to not only benefits in latency, it also gives a lot of improvement in terms of the bandwidth for medium and large message sizes. And with this, you can get very good end application level performance. This is like a Humdi Blue, which is a molecular dynamics application. So here you can see, compared to the basic design, the MVAPICH2 GDR gives almost like a factor of 2 improvement. And those are the point-to-point kind of things. The latest release actually also introduced the non-blocking collectives. Just like I indicated earlier from the host, you can actually do non-blocking collectives from the GPU buffer. So that means you initiate the collectives. Here we are showing I all to all and I gather. You can actually get very good overlap, almost very close to 100% when trying to move the data from GPU buffer as well as trying to overlap with computation. So this MVAPICH2 GDR version here, there is as the technology is maturing, you need some different pieces of the software. You need a specialized Mellanox version, NVIDIA driver, plugin for GPU direct RDMA. There is also a newer module called GDR copy. So we encourage all of you to just download all these things and download our stack, and you should be able to directly run it. And we also have, like, some people have not moved to the Mellanox OFED. So for them, actually, we have a newer version, which is, we call it GDR with no GPU direct. So you can actually still run our stack, the MVAPICH2 GDR. It has a lot of other optimizations. You can use it on those kind of systems to get better performance benefits compared to even MVAPICH2. So if you have any GPU cluster, we'll strongly suggest you to move to this version. So in this stack also, we have different kinds of parameters. I'll very quickly go over it. There is like a MV2 use CUDA, that is a fundamental parameter. It is disabled by default because some of the people also run, using this MVAPICH2 GDR, also purely run host-based operations. And since this CUDA over MPI has some pointer checking, has some overhead, so by default we disable. So if you are using this stack for pure host communication, that is good, but as soon as you start using the GPU communication, we suggest you to enable it. And similarly, there is another CUDA block size. Currently it is 256 kilobytes. Especially if you have large data being transferred, you can actually tune it to 512 or 1 megabyte. It will vary based on your CPU platform, InfiniBand, HCA, GPU, CUDA driver version. You can play around with this parameter to get the best performance. So then to enable this GPU direct RDMA technology, this is enabled by default. We also have a GPU direct limit because as I indicated earlier, like because of the chipset limitations on different platforms, you may see some trade-offs in performance. So we have a GPU direct RDMA limit. Below that limit, we use one kind of protocol. Above that SSI, we use another protocol, so that also can be tuned to match with the communication characteristics of your applications. So then we have this IPC support. That is like the best communication between the GPUs within the node. These days we see like people are deploying clusters with 8 GPUs, 16 GPUs per node. So that you can again play around here with MVAPICH2 CUDA IPC. That is enabled, but CUDA SMP IPC is disabled. It has benefits of device-to-device transfer, but in some platforms it hurts the device-to-host, host-to-device transfer. So if you are primarily doing device-to-device transfer, as the figure indicates, SMP IPC will give you the best latency, so you can actually turn it on. So those are the kind of the samples I took from MVAPICH2, MVAPICH2X, MVAPICH2 GDR. to illustrate some of the optimizations, but of course, we have similar kind of things for the MVAPICH2 mic, MVAPICH2 virtualization, energy-aware things. All these things are indicated in our user guide. So I'll strongly recommend you to refer to that. Depending on the version you are using, you should be able to optimize and tune it further. Now, to wind up this presentation, I just want to indicate like this is a new effort which we have started, as I indicated, like jointly with several of the organizations like TAC, SDSC and OSC and OSU. So as you saw, like a lot of these parameters are there. Tuning a set of parameters can actually help. So our objective is to bring the community together to compile a list of such contributions as best practices. So initially we have done for these 8 applications. I'll show it very quickly in the next several slides. We are continuously soliciting additional contributions, and so that please feel free to, if you have used some of this tuning on any given platform, please send us those data, and then we should be able to link it at the MVAPICH site while providing credits to you, so that the community people can actually again take a look at it, and they can actually then need not go through all the exercises again, but try to get the best performance for their applications. So let me quickly go over these 8 case studies we have done. This is Amber. It has been done by Dong Choi from San Diego. So here, if you see, I talked about that eager threshold parameter. There is also another parameter called VGOF total. By adjusting those using MVAPICH2 2.2b with 256 process, you can see you can extract 19% improvement in the overall execution time for Amber. And the input files were used here, the MDIN and PM top. So similarly, this is a mini AMR. So this was done by Karen Tomko and Dong Choi from OEC and UCSD respectively. Here again, similarly playing around with these 2 parameters, you can see around 8% reduction in the total communication time. So then this is a SMG 2000. I talked earlier about the impact of transport protocols like RC and UD. This study was done by Jerome from TAC. So here you can see that by instead of using the default, which is the RC protocol, if you use the UD protocol with the particular flag MV2 use only UD, you can see almost like a 22% benefits in a 1,000 core run of SMG 2000. The next one is the Neuron. This study has been done by San Diego Supercomputing Center, submitted by Mahidar. So here again, you can see the similar UD protocol actually helps up to 1,024 processes. You can see you can get a 27% improvement in the overall execution time. This was done with this specific input file, and this ran on the Comet. So in one aspect I didn't indicate earlier, which is like a collective tuning. I just indicated the point-to-point tuning, but we have been working on a lot of collective tunings over the years. Especially when you are running MPI and OpenMP programs, people try to use different kinds of number of processes per node. So you can have PPN2 or PPN, let's say 8, 16, depending on your number of cores per node. So this study was done for HPCZ by Jerome and Carlos from TAC. So here you can see that on a 512 core HPCZ, using 8 OpenMP threads for MPI process, we can get around like 24% improvement. And similar kind of study was done for the second one, which is for Lules. Again, it was done by Jerome and Carlos. Here you can see that for PPN2 process per node, the tuned version of the MPI reduce shows around like a, here 4% improvement on 512 core, and on a 2K course we can get around 51% improvement. So these are the kind of the tuning study we have done, and as we learn from the tuning studies, we actually incorporate some of these things internal to our stack also. So then this is a milk application. I didn't have time to go over a newer scheme introduced by Mellanox, which is supported in our library, called user mode memory registration. So this is good for applications which have a lot of data types. So here you can see, using the MVAPICH2X with the milk around 640 processes, you can get around 6% benefits by just turning on this new flag, which is MVAPICH2 use UMR. So this study was done Ming-Jae Lee from OSU. So then earlier I indicated also the Humdi Blue, just to repeat here. So this is again from using the MVAPICH2 GDR code base, and using this CUDA as well as GPU Direct and GDR copy, you can see like you can improve the throughput of this application by a factor of 2. So these are some of the kind of the case studies we have done so far. And as I indicated earlier, we look forward to contributions from the community so that we can put all the best practices together, and people can always refer to these kind of tuning studies to exactly use similar kind of tuning for their runs. So with this, let me conclude here. So in this talk, I provided an overview of the different MVAPICH2 software libraries, then took at least 2 of the stacks, MVAPICH2 and MVAPICH2 GDR, based on the timing constraint. And I showed some details on the configuration and runtime parameters and how you can optimize. And I also demonstrate the best practices. Of course, a lot of details are available on our user guide. We also have the open MVAPICH discuss mailing list. So we encourage people to ask questions there. So just to conclude, as I started with this project, we started in year 2000. So we have been going almost like 16 years now. So this is like our plans for the Exascale. Currently, we have scaled our library to 500,000 cores. Our next goal is to go to up to 1 million core. And on the hybrid programming, we have plans to support for task-based parallelism, the UPC++. The basic UPC++ support is there. The next one, we want to move to the task-based parallelism. Similarly, the user mode registration, on-demand paging. We are looking forward for Omnipath, night slanning, and extended RMA topology-aware sub things. We are also working a lot on the MPI tools interface. Those are already available in some of the releases. I just didn't get time to talk about that. Similarly, on the fault tolerance, we also have support for SCR. So with this, let me thank our sponsors. But besides the sponsors, I'd like to thank all the people who have contributed to this project over the last 16 years. This consists of all the past and current students, staff. So they do all the work, the hard work. So they are the actual heroes of this project. So with this, let me stop here. And if you have any quick questions based on the available time, I'll be happy to answer these questions. Otherwise, we can also have the discussion offline and try to answer your questions. Thank you.
Thank you so much, DK. I'd like to open the floor for questions now. I think if you've been muted, I think you can unmute yourself if you have a question. Any questions? Okay. I have one for you, DK.
Sure, please.
So the study you're doing for the applications made me think about how we install these applications here at TAC. And I'm wondering if the results are general enough that we can preset these environment variables when, say, someone loads the Amber module. Mm-hmm. And you just sort of automatically improve their performance without them knowing what we've done.
Yes. I mean, that is our next step, actually. We have discussed this with Bill, Jerome from TAC, and as well as from SDSC. So in fact, that is our next goal. Based on these studies, if we can generalize it, we want to take it to we call it like an application-specific tuning. So, but we'll need help from people like you and other the system administrators to put the right parameters there so that the users don't need to be burdened with that.
So are you considering doing like binary signature detection, or just looking at the name of the executable, or Just providing guidelines for sites such as ours.
I think we can start with some simpler schemes. For example, Stampede, we know the characteristics. So if we make several runs and we see some consistent behavior for a given like Stampede, we can set it up in a simpler manner.
Mm-hmm.
Because we don't want sometimes to go into a like a false positive also, right? We don't want to do things which will hurt sometime also.
Right. That's what I'm worried about. If our test cases aren't broad enough, we might impair performance instead of improve it.
Yes, yes.
Are there any other questions? No? Okay, well then I'd like to thank DK again for making this presentation. I've learned more than a few things, which I hope will help me with the upcoming architectures we're getting here. But thank you so much.
Okay, thank you.
Thank
All right, everyone. We'll have another symposium in about a month. Thanks.
Thank you.